So dear students, in this video we are going to do a new topic. So our topic for today is torque acting on a dipole when it is placed in an electric field. So torque acting on an electric dipole when it is placed in an electric field. Or in other words, it can also be said like this. A dipole will experience a torque when it is placed in an electric field. So our wish here is to calculate what is the value of that particular torque. So we already have a knowledge about torque from our previous classes. So torque is basically, it is a rotational analogy of force, or in rotational motion a force is replaced by torque, and it is sometimes also known as moment of force. And torque is a vector quantity. That means it has both magnitude and direction. So let us get back to our topic. So let us draw electric field lines towards this direction. So these are electric field lines, or rather uniform electric field lines. Now let us place an electric dipole in this uniform electric field. So I have placed an electric dipole in this uniform electric field whose dipole moment is directed from negative charge to positive charge. It is directed from negative to positive charge, and which is indicated by P vector. Now let this angle theta be the angle between this P vector and E vector. So this is my E vector, electric field vector, towards this direction, and this is my dipole moment vector towards this direction, and I have indicated an angle between them by theta. So theta here is angle between dipole moment vector and electric field vector. So what will happen now? So we have two independent charges in a dipole. They are positive Q and negative Q, and we already have an idea that charges, any individual or independent charges, will experience forces when placed in an electric field. That means this positive charge will experience a force independently, and even this negative charge will experience a force independently due to the influence of this electric field. So, and we know that a positive charge will always experience a force towards the direction of electric field. That means this positive charge will experience a force towards this direction, towards the direction of the electric field, and which can be written as force is equals to charge multiplied by the value of the electric field. So this is the force experienced by the positive charge, and it is directed towards the direction of electric field. That's why the direction of the force is given by the direction of the electric field. So force is directed towards the field. Now, here is a negative charge, and we have an idea that a negative charge will always experiences a force opposite to the direction of the electric field. So electric field is directed towards this direction. That means this negative charge will experiences a force towards this direction, which is the opposite direction to the direction of the electric field. That means the value of the force will be given by the magnitude of the charges into electric field, but here will be one negative charge, which indicate the direction of the force is opposite to the direction of the electric field, because electric field is directed towards this direction, hence force is directed towards this direction. So this negative sign will indicate force and electric field are opposite in direction. But the magnitude of this force and this force will be same here, because the magnitude of the two charges are same and they are placed in the same electric field. Now, if you look closely to this situation, I have a dipole, system of a dipole, and two poles of the dipole are experiencing force differently. This pole is experiencing a force in different direction, and this pole is experiencing a force in different direction. That means something is going to happen here. And this force, and dipole, this line of the dipole are not collinear. If they were collinear, then there will be no any translational motion and rotational motion. But here is this force makes some angle with this particular line of dipole. Hence, there will be some rotation. And what will be the direction of this rotation? How this particular dipole will rotate? So that is we are going to calculate here. So it will be simpler if I resolve this force in two particular directions. One towards the direction parallel to the dipole moment. This is direction parallel to the dipole moment, and this is a force perpendicular to the dipole moment. So I have resolved this force into two directions, one parallel to the electric dipole and one perpendicular to the electric dipole. And if this is theta, this will be my theta, because this is a straight line. And if this is theta, this is QE, then this particular force will be my QE cos theta, and this particular force will be my QE sin theta. Similarly, I can resolve this force into two directions, one parallel to the dipole moment in the same line of the dipole moment, and if this is theta, this will be my theta again, because this will be my theta. If this is theta, this is theta, and this is also theta, and this will be my perpendicular component. So if this is theta, I have resolved this into this component and this component, so this will be my QE cos theta in this direction and QE sin theta in this direction. So its direction it will be in this direction. So vectorially, if you represent it, so negative sign will comes into play. So that's another thing. So let's see here. Now if I resolve the two individual forces, I got four forces, independent forces, one towards this direction, one towards this direction, one towards this direction, and one towards this direction. And now this QE cos theta and this QE cos theta lies in a same straight line. That means this QE cos theta will pull this in towards this direction, and this QE cos theta will pull this in towards this direction. That means its effect will be perfectly cancelled by its effect. That means QE cos theta got cancelled by this QE cos theta. So the only force remained here is QE sin theta and QE sin theta. So this is my dipole, and one QE sin theta is pushing this dipole towards this direction, and another QE sin theta is pushing this dipole towards this direction. So what will happen if you push this end upward, and if you push this end downward, then what will happen? It will going to rotate. So in this case also, this dipole will be going to rotate towards this direction, because this is pushing and this is pushing upward. This is pushing downward and this is pushing upward. So this dipole is going to rotate this way with some axis of rotation, which will be the midpoint of the dipole. So axis of the rotation will be midpoint of this particular dipole. So it is going to rotate. Now, what will be the value of this rotation? What will be the moment of this rotation? So that moment of rotation is also known as torque. So we are going to calculate the value of the torque in this particular case. So torque will be simply one of the force, that is QE sine theta. So one of the forces QE sine theta, and the distance between these two perpendicular forces is 2a. So this is basically one of the perpendicular force, multiplied by 2a is the distance between the perpendicular forces. So this is the definition of, or the formula for the torque forces. So one of the perpendicular forces QE sine theta, either this one or this one, multiplied by the distance between the two perpendicular forces, nothing but 2a. So 2a is the distance between the perpendicular force. So torque will be basically torque will be represented by tau. This letter is a Greek letter for T, and it is pronounced as tau, T-A-U, tau. So tau vector, which is a torque vector, it is a vector quantity. So torque vector will be QE sine theta into 2a. So this gives me tau is equals to Q into 2a is nothing but it is a magnitude of the dipole moment, Q2a. P is equals to Q2a, magnitude of the dipole moment, into E sine theta. Now this is a known relation or a known formula for us, because PE sine theta can be written as a vector multiplication of two vectors, that is tau is equals to P cross of E. So P cross of E is basically PE sine theta. That means this particular torque, the value of the torque will be P cross E, whose magnitude will be P sine theta, and whose direction will be given by the cross product between P and E, that is tau, direction of the tau. So this is your torque acting on this particular dipole. Now what is the direction of this torque graphically? So if I see it here, so what I have to do is I have to put my this four fingers along P, and I have to curl towards E. Then this thumb will give me the direction of this particular tau. So here, this is my C. This is the direction of my P, dipole moment, and this is the direction of my electric field. So if I put my four fingers towards the direction of this dipole moment, if I curl it towards the electric field, that will be my P cross E. Then the resulting thumb will give me the direction of my torque. That means in this case, P cross E gives me the direction of the torque inside this paper. So torque is basically directed inside this plane of the paper. So that is the direction of the torque, and the magnitude of the torque will be PE sine theta. So let us discuss some special cases here. Number one, if this is my electric field, and if I place my dipole this way, this is my dipole, whose dipole moment vector is from negative to positive charge. So in this case, the angle between P and E is 0. Theta is 0 here, because P is directed, P and E are directed along the same direction. That means theta is 0. And what will be my value of torque? Torque in this case will be PE. The magnitude of the torque in this case will be PE sine 0. And sine 0, we know sine 0 is 0. So torque will be 0. That means when I placed a dipole in an electric field this way, such that electric dipole moment and electric field are directed towards the same direction, then this particular dipole will not experience any torque. That means this dipole will not rotate in this case. It will be like this forever. Case number 2, when the dipole is placed this way. This is my electric field. And if I place dipole this way, this is my negative charge and this is my positive charge, and dipole moment is from negative to positive charge. So in this case, P is in this direction and E is in this direction. They are opposite in direction. That means theta will be 180 degree. So tau will be PE sine of 180 degree, and it will be again 0. Because sine 180 is also 0. So in this case also, this dipole will not experience any torque. Now third case, this is my electric field. These are my electric field lines. And if I place dipole this way, this is my negative charge, this is my positive charge, and dipole moment is directed from negative to positive charge this way. So in this case, the angle between the dipole moment and electric field is 90 degree. So theta is 90 degree. So in this case, torque will be PE sine of 90 degree. So sine 90 is 1. So torque will be P into E. So this is the maximum torque possible. So in this case, the particular dipole will rotate with maximum torque. Or even you can put it this way. This is the negative charge. This is the negative charge. This is a positive charge. So P is in this direction. And the angle between, now angle in this case will be 270 degree. 270 degree. Earlier it was 90 degree, but in this case it will be 270 degree. Earlier it was 90 degree, and in this case it will be 270 degree because P is downward. So even in this case, theta will be 270 degree, and tau will be PE sine of 270 degree, and tau will be again 270. Sine 270 is again 1, so torque will be maximum. So it will experience again a maximum torque. So if I place a dipole either parallel or anti-parallel to the electric field, then it will not going to rotate because it experiences a 0 torque. And if I placed electric dipole perpendicular to the electric field, then it is going to rotate with a maximum torque. So this is it for today. Thank you.